All right, let's dive right into this explainer. Chemistry isn't just about mixing colorful liquids in a beaker and hoping for the best. It's really about highly structured investigation. We're basically acting as molecular detectives here. Today, we're going to walk through this totally fascinating method where we use what we do know to figure out exactly what we don't know.
So picture this. You're handed a completely random piece of metal. No labels, no hints, literally nothing to give it away. How do you identify it? Well, today we're going to learn exactly how to deduce its identity using a really clever technique. No guessing required. It's a precise, logical deduction where we actually look at what's left behind rather than just directly measuring the metal itself. Pretty cool, right?
Here's our game plan for the explainer. We'll start with the unknown metal mystery, unlock the secrets of back titration, prep our lab toolkit, execute the procedure, crunch the chemical clues, and finally, identify our suspect.
Section 1. The Unknown Metal Mystery. Establishing the Objective.
Our lab manual sets up a really clear two-part mission for us. First up, we have to establish a rock-solid baseline by standardizing our acid. Then, we use that exact same acid to interrogate our unknown alkaline earth metal, which we're just going to call M for now. And here's the thing, without step 1, step 2 is completely meaningless. We need absolute precision.
Section 2. Unlocking back titration, the interrogation technique.
All right, this brings us to back titration. The best way to think about this, it's kind of like handing a cashier a $20 bill for a really cheap item, and then counting your change to figure out exactly what the item cost, rather than trying to, weigh the coins beforehand. We're going to throw a massive calculated excess of acid, our $20 bill, at our metal. Then we just measure the leftover acid, our change, to figure out exactly how much was consumed. Make sense?
And here is our crime scene. Mathematically speaking, the stoichiometric equation. Our unknown solid metal M completely dissolves in that calculated excess of aqueous hydrochloric acid. It bubbles away, produces hydrogen gas, and leaves behind unreacted acid. That leftover acid, sitting right there in the flask, that's the critical piece of evidence we're going to measure.
Moving on to Section 3. Preparing the lab toolkit. Gearing up.
Every good detective needs the right gear. We're arming ourselves with precise measurement tools, like a 50-milliliter burette for dropping liquid with pinpoint accuracy, and a 25-milliliter pipette for exact volume transfers. Alongside the glassware, we've got our key chemical reagents, hydrochloric acid, sodium hydroxide base, and our trusty chemical informant, the phenolphthalein indicator. This stuff is great. It'll magically change color to visually alert us the exact split-second neutralization happens.
Section 4. Executing the procedure. The investigation.
Okay, stage 1. We got to make sure our $20 bill is actually worth $20. We fill our burette with the sodium hydroxide base and pipette exactly 25 milliliters of our acid into a flask. Then we carefully drop the base into our acid until that magical pale pink color hits and holds for exactly 30 seconds. That specific color change, that tells us the exact standardized concentration of our acid toolkit. We're dialed in.
Next up, the real interrogation begins. We clean our metallic suspect, weigh it down to the tiniest fraction of a gram, and drop it into 25 milliliters of our newly standardized acid. We let it react completely. Once it's fully dissolved, we add our phenolphthalein, and then we measure the change, the unreacted acid left over. We do this by titrating it again with our base. The volume of base we use tells us exactly how much acid survived that initial reaction.
All right, Section 5. Crunching the chemical clues, data and math.
So, looking closely at our datasheet for standardizing the acid, the crucial point here is meticulous record keeping. We have to record our initial and final burette readings to lock down the exact volume of sodium hydroxide used. And notice, we don't just do this once. We do a rough gross run and then precise runs labeled I, and II. Why? Because we average these out to ensure our baseline acid concentration is absolutely bulletproof. Now, moving over to the reaction data, we map out the exact mass of our metal samples. Right below that, we record how much base it took to neutralize the leftover acid. Again, notice that we run this for two separate samples, sample I and sample 2. This redundancy is key. It verifies our results and sets us up perfectly for the final logical leaps.
Okay, this step-by-step logic trail shows exactly how we pull the whole shebang together. Steps 1 and 2 give us the total starting amount of our acid. Step 3 uses our back titration data to tell us how much acid survived.
For step 4, we simply subtract the survivor acid from the total acid. Boom! That difference is exactly how much acid reacted. Then, using that 2-to-1 stoichiometric ratio from our earlier equation, we zero in on exactly how many moles of the metal were actually in the flask. Divide the original mass by those moles, and you've got your molar mass. By averaging the molar mass calculated from our 2 samples, we finally arrive at the single most important number in our entire investigation. Averaging smooths out any of those tiny, inevitable human errors from the lab, giving us a highly reliable, rock-solid chemical fingerprint for our unknown suspect.
Which brings us to Section 6, identifying the suspect, the reveal.
This is it, the moment of truth. We take our hard-won average molar mass and visually scan the alkaline earth metals on the periodic table to find our match. Is it magnesium, sitting at roughly 24 grams per mole? Maybe calcium, at 40. Strontium? The math is going to point directly to one specific box on that table.
And I'll leave you with this thought. If you were standing in the lab right now, watching that pale pink color appear, running the subtractions, and deriving that final atomic weight, once you calculate that final mass, which specific element on the periodic table will stand revealed as our mysterious suspect, M? The beauty of chemistry is that the answer is always waiting right there in the data. Keep questioning, keep analyzing, and thanks for joining me on this explainer.